Yeah, like Jim mentioned, Shankar Srinivasan. I used to be with the group. Right now I've moved on to take a position with Iowa State Extension and Outreach. But I had committed to talking about this, and I'm here to enlighten everyone about processing this stuff, whether it's a nightmare or was it a cakewalk. Well, all of us from Iowa State have been talking since morning, and you might be wondering what's he got. Does he have anything new to talk about? In reality, not. So I'm just going to repeat some of the material which was covered by Dr. Gould, Dr. Schrader, and Dr. Madboli, but top it off with some practical experiences of working with this material. So the bad news is, since all of these materials have been covered, I don't have much to talk. The good news is that shortens the presentation to 15 minutes. So with that, I'll start moving ahead. Once we started this project, especially during the stage 1 or round 1, am I moving out of frame and then coming back in? Okay, maybe I'll try to stand still. When we came up with these different classes of materials, we wanted to categorize them in a broad manner so it's easier for us to keep track of these materials and process them as separate classes. And these were the three primary classes which we came up with. One was the protein-based materials, another one was fiber-based containers, and the last one was carbohydrate-based. I should say that what carbohydrate here means carbohydrate derived materials, which could be PLA or PHA. Basically, we take the carbohydrate from corn, convert them into sugar, and then we convert them into plastics. So with that, this is a perfect example of what happens when you put a bunch of scientists with 2 pots of coffee in that room. Everyone come up with new and different ideas, and you end up with such a yay big list of materials to process. So well, actually I think the project did outline 30 materials, and there were 2 more which are not listed here, which we ended up processing, but it was fun going through this. And just for the sake of highlighting things, the dip coated ones are the ones which are boxed out here, and the reason for that, I'll come to that later in the presentation. So once we had all of these 30 materials in our bags, okay, how are we going to go around processing all of these, keep a track of every single material? We had to start thinking like industrial engineers, come up with process flow charts and things like that. And this is a very aggregate process flow trying to represent how we went through processing these materials. And what I'm going to spend a little bit extra time today is going to be on the protein compounding part. So for the parts production, as you saw, we had protein, carbohydrate based, and the dip coating based. For the protein based, we had to do 2-step compounding process where we compounded the protein material ahead of time to form a pellet. And then as a second stage, we compounded it with the bioplastic resin, which would be the PLA or the PHA, to form a blend at the end. Also, another side path was, using ag additives. I just use that as a broad term, denoting the DDGs or the stover which was used. So all of those were brought together in a second or third stage bioplastic compounding. And once we got the resin, we injection molded them, which either went directly to trials or to dip coating and then further drying. So like I said, I'd be spending a little bit more time on protein plastic compounding. The reason being is, fiber inclusions or ag additives, industry has done quite a bit, like wood fiber based plastics or such. There's been some sort of a process flow that has been established, but not much has been done in terms of protein plastics commercially or even in terms of trials. So I thought it'd be helpful to talk a little bit more about that. What these protein plastics are nothing but, you take soy protein powder, it could be soy flour, soy protein isolate, varying the protein concentration, mix them with plasticizers, salts, water, in a big industrial grade food mixer, And once you mix all of these, it becomes almost like a powdery dough, which we would take and extrude with a twin screw compounder at a certain temperature to get these pellets. And Dr. Gruel used to attribute most of my health because of this particular activity, because a lot of this material was missing towards the end of the trial. I was blamed of trying him out for dinner. So, but in reality, they didn't taste nice. I do agree that I did eat some of it, but so once we got all of these protein plastics compounded, you had to bring them down to a certain moisture level. In plastics compounding, everyone knows that moisture is one of the parameters to control, and having compounded these protein pellets with high moisture content of almost up to 30 to 40%, we had to bring them down to 5 to 6% range so that they are both plasticizable and at the same time they can blend with other materials like PLA or PHA and such. So once we got it to that particular stage, we would compound them and get the final resins, which would either be a blend of PLA protein, PLA DDGs, or PHA DDGs, and on and on and on, basically the 30 different materials which you saw earlier. Now, there was a certain process which I have not talked about here a little bit, was the PLA in particular had to be pre-processed. By that what I mean is the melt temperature of PLA is quite high compared to these protein materials. So in order to avoid these protein materials from burning, we had to suppress the melt temperature of the PLA by using PEG or a plasticizer to bring down the temperature. Hannah, you had a question.
Yeah. What does it actually mean, compounding?
Compounding is an industrial term of use. It's an industrial term used to indicate mixing two different plastics, polymers, or components.
Oh, I see.
So, yep, you would not call it an extrusion house. You would call it a compounding house. So that's the reason I'm trying to use as much colloquial industrial terms here as much as possible. Yeah, once again, going back to the point, some of the materials had to be suppressed in terms of processing temperature so that they could accommodate the other material. For example, PLA would melt and you would have good melt flow at 190, 180 Celsius, whereas the protein plastic or the protein resin would start degrading around 140, 150-ish. You don't want to stay, you don't want barrel residence times of 5 minutes and above for those particular materials. So at the end, what will happen is if you have this temperature mismatch, you would basically get charred compounded material at the end, which is not desirable. So once we got all of these resins, we took them down to some of our partner molding houses down in Missouri, Kansas City. Initially, especially like what Jim mentioned earlier, with the high protein content plastics, we had to come up with a way of demolding them without breaking them, because the green strength of these materials were not that great, nothing compared to polyethylene or even low density polyethylene. So what we had to do was come up with a mold which actually has a false bottom. So what will happen is these three pieces would close and then the plastic would be shot through this injection gate. Once the part is formed, typically for those materials the shrinkage was not as much, so it would stay on the cavity side, and what we had to do is let this base plate open and we would literally slide in our hands and pop it off. That's what we had to do for the high soy content ones, but that was not the case with soy PLA blends or soy PHA blends, where typically it would stay on the core side, which is what you would want to either have ejector pins or stripper rings so that you can go with a high production rate or mechanized process. And Dr. Gruel already used this schematic. This was the 3-piece mold which we used. We came up with, we almost became Egyptians. We started building pyramids of pots, and that was basically our first round of 30 different materials.